Okay, we're giving it the usual couple of minutes here while we wait for folks to come on in, and then we'll get going. Okay, that's probably our usual crew, I'm guessing, right? Um, nice to see me right the whole time. Okay. All right, let's get into it. So last time I believe we left off. Or actually, here, wait, before I just um before I just drop everything back into lecture mode, it seems worth starting the class by noting something that hopefully everyone saw in their announcements. Mainly, homework due dates have been changed. Everything is in your favor. All I've done is I've moved things from Friday nights to Sunday nights, so people have a little bit longer if they need office hours. Since I think I've mentioned this before, I'm teaching at night, working during the day. This is very helpful since it's kind of hard to set up office hours during the middle of the work week, and this gives us the weekend potentially to work together on that. So everything's in your favor. If you want, you can still turn everything in on Friday, no problem there. But you can just also take till Sunday if you feel like it. So if there's any questions on that, shoot me an email. If not, I don't know why there would be. Cool. Enjoy not having to turn in your homework quite as early. That's a that's something that I think everybody likes. So with that, let's jump back into lecture world. Um, so last time we there we go. We dropped off talking a little bit about Cauchy sequences and some various notions of uh, convergence, these kinds of things. What I think we were talking about last time, if you recall, was we were talking about sequences. Sequences, you can denote them with parentheses z sub n. Some people will also put like subscript n equals 1 to infinity or something like that to denote what the n ranges over. It's also perfectly fine just to do z sub n. Normally this means 1, 2, 3, 4, but z1, z2, z3, z4, so on in the usual way. Sometimes people start it with z naught. We're just not doing that here. All of it amounts to reindexing, and it's not a big deal. So we'll say a sequence of points converges to a point z0 if for all epsilon greater than 0 there exists a natural number n greater than 0, such that for all little n greater than or equal to this big N, then z sub n minus z naught is less than epsilon. That means, it always sounds technical when you say it at first. All it means is that, like, hey, if you go out, and we drew a little picture here, if you have your sequence and you go out far enough in the sequence, all but a finite number of terms at the beginning are within a distance epsilon to your desired point. And this holds for any epsilon you choose. All right, so that was a straightforward little thing. We've probably seen this before. If you haven't, don't worry. It's kind of annoying to state it at first, but these epsilon arguments are never too. I won't make you do hundreds of them. Don't worry. They're important, but they're never too central to the rest of the material. They are central on a technical level, but not in the formal high-level presentation of it. Then we talked about Cauchy sequences. These are sequences such that for all epsilon greater than 0, there exists a big N, a natural number greater than 0, such that z sub little n minus z sub little m is less than epsilon in norm in magnitude whenever n and m are greater than big N. So this says a Cauchy sequence is just a sequence where no matter what distance you choose, you can always go far out enough in the sequence such that all of the terms after that are within that distance of each other. Meaning that it just gets, they get super close together, kind of like this picture we drew here, where they can maybe like ranging way out there, but then they start getting really tightly packed together and they never get any further apart, right? And that's the idea of a Cauchy sequence, i.e. like all the terms after some point get as close as you want. And so it seems like Cauchy sequences, if any sequence converges, a Cauchy sequence should converge. And this is not the case in every single possible situation in mathematics, not the case in every possible nice topological space induced by a norm or some notion of metric, some way of measuring the distance between points. But in C, in the complex numbers, this is the case, and this is a big deal. This is a big, important fact in your book. It doesn't bother to mention it as a theorem, but it is similarly important that it should be stated as one. Although then maybe they would have to prove it, and we won't. So this is a fact stated as a theorem, and we won't prove it. But every Cauchy sequence in the complex plane converges. This is the so-called the completeness of C. So the complex numbers are complete. The real numbers are also complete. Many familiar spaces are complete. It just means that they have the limits of all their Cauchy sequences. So this is a very useful fact. We will use that occasionally. It is great. So overall, though, we've been talking about continuity. I still have the definition up here from last time. Functions are continuous if they preserve limits. And this is the same with sequences. That is, if a sequence z sub n converges to z naught, then a continuous function has to satisfy f of z sub n, that sequence, converges to f of z naught. So convergent sequences are preserved under continuous functions the same way that continuous functions preserve limits. And this is an equivalent definition. You could say that a function is continuous if and only if every convergent sequence of points is mapped to a convergent sequence of points. That is, if f of zn converges to f of z naught whenever zn converges to z naught. And so that's a classic, wonderful result, but we need to move along from this sequence point into a few other things, since this section is monstrously long. So let's keep going. After the discussion of sequences in your textbook, we jump into a discussion of closed sets. So I'll state this very generally. Let's let x tau be a topological space. A subset C contained in X is said to be closed if its complement is open. And so there are a few different ways to write complements. How we're going to write it is we'll write it as X and then we'll do this little without sign. X set minus C is open. That is, if it's an element of tau, the topology on X. So closed sets are the complement of open sets, and it sounds like it's just so obvious, like, oh, okay, well, if it's, think of it like this, if you've got, you've got everything except for, here, actually, let's not even do it in R2, let's do this in just straight up R, right? If you've got 0 to 1 and you're not including the endpoints, and you're looking at this as a subset of, say, like R, right? That's open. So naturally, we should expect, if we're going, say, from like minus infinity to 0, and then maybe like, union 1 to infinity. Something like this would be say that this is closed, or, ooh, suddenly that seems more difficult. So should we define closed sets as the complements of open sets, or should we define open sets as the complements of closed sets? Are these the same things? It's not always super clear that when you're starting to look at everything in this fashion that you get a nice division of your space, or all the subsets of your space, in just this is closed or this is open, right? You can have things that are both closed and open. For example, consider the entire set X. We know that X is an element of, oops, I should have said element of, sorry. I just realized that I made a mistake down there. I wrote contained in instead of element of, my bad. We know that X is an element of tau. So notice that the empty set is, or X set minus the empty set is just X, right? And that's still, well, that's in tau. And the empty set is closed. But the empty set is also in tau. So it's open and closed. Similarly, we can do this slightly differently with X set minus itself, which is the empty set, and that's an element of tau. Hence, X is closed. But X is also in tau because it's the whole space. So there are sets that can be open and closed. There are sets that can be neither. It is a little bit more than just like, okay, well, here's all the subsets. Here's one bag. Here's the other bag, right? But all things considered, it is a perfectly workable concept to talk about sets being closed and define everything in terms of closed sets instead of open sets. Nothing is going to get broken here. So we have a nice proposition that I will carry on over from the text. All right. Okay, so here's a proposition. Let's jump into this guy a little bit. Proposition 1.4.7. Here we've got some nice ones. Some of the things I just went and looked at with that. The empty set is closed. The entire complex plane is closed. We just basically went through that for both of those. Necessarily, the empty set and the entire space must be closed in every topological space, then they also must be open. Then we also have the intersection of any collection of closed subsets of C is closed, and the union of any finite collections of closed subsets of C is closed as well. Notice, and I'm going to maybe be mildly annoying by jumping way back to this. It went in the very first thing we did when we defined a topological space and a topology. Notice a topology on a set X was just a collection tau of subsets called open sets, satisfying like the same two things, right? We had X in the collection of open sets and the empty set in the collection of open sets. And then we had any union of elements of tau is in tau, and any finite intersection of elements in tau is in tau. Notice, all that we were doing in the topology definition, we could have equivalently done with closed sets. That is, we could have said, instead of the intersection of any finite collection of open sets is open, we could have said the intersection of any collection of closed subsets is closed, and then the union of any finite collection of closed subsets is closed. So we basically just switched closed or open to closed, and then we switched unions and intersections. Does that make some sense? We complemented the things, sort of. We did it backwards, and it worked just fine. It's the same thing. This is, you could use this just as equivalently to define a topology. It's the proposition is like vacuously true in that regard. It is equivalent to the definition of a topology, and it's totally reasonable to go through and prove it. It's not like trivial at all, but it is a good way to exercise your skills dealing with open and closed sets. But these guys are important for the relationship to continuous functions and to sequences and a bunch of other things we're going to look at in a little bit. In particular, it'll be useful when we're talking about compactness. And this is probably the easiest way to talk about closedness in C or R2 or R or Rn or Cn. And this is proposition 1.4.8. This is another way you could go through and define closed sets. It'll end up being equivalent in C. We'll say that a set is closed if it has all of its limit points. That is, if you have a sequence of points in that set that converge to some point, then that point also belongs to the set. So you can think of this really easily. Just imagine yourself having like a open circle or something, right? So all of everything in here. And then we have some sequence of points, and it maybe like gets really close to something right on this boundary of it, but we don't actually have that point right at the edge, right? So this is like an open set. You go right up to where it is. Everything in that sequence is in there, except at the very end, the thing it goes to, it's not in there, right? And so it doesn't have to be the case that every set where you can find a sequence that converges to something outside of the set is open, but it's certainly not closed. This just means, the closedness just means that any sequence that converges to something in the set. It's the easiest way to think about it. And so there you go. Closedness. All right. So this is why we have to care about closed sets. It's a useful way to talk about convergence and nice things like that. So there's I'll skip this one. There is so you know how we defined, they make this an entire proposition in your textbook. I won't even state it here. It's proposition 1.4.9. We defined continuity a while ago so that f from, or I won't even repeat it here. I won't rewrite the whole thing. I think I just have it. There we go. Okay, so yeah, given a topological space x tau and y nu, we say that a function f from x to y is continuous if the pre-image of any open set is open, right? So the pre-image of O is in tau whenever O is in nu. Okay, so we took this as the definition. Proposition 1.49 says that the following are equivalent. F is continuous, the inverse image of every closed set is closed, and the inverse image of every open set is open. So all they're doing here is they're saying, okay, you can do exactly like what we just defined openness and closedness by, and there is nothing, or you can just do exactly what we defined continuity by, and there's nothing that's broken when you switch to the equivalent closed set definition of a topology, which is basically what they are giving you here. This is just a closed set definition for topologies as opposed to the open set definition. And so naturally you can formulate continuity in the same way. It is worthwhile to go through the proof, though, of proposition 1.49. It is highly useful if you are not familiar with epsilon delta arguments. I highly recommend going through and looking at how that looks, right? In particular in an abstract case, because it doesn't involve like calculating some epsilons and deltas for something specific, but it still involves using them. And so that's a very useful fact. They, of course, say that the same thing holds for relatively open and closed sets, right? But since we defined everything for arbitrary topological spaces, this is an immediate and obvious consequence, and we don't even have to worry about doing it in this sort of roundabout and silly way where we have to state the same thing multiple times in a row. Instead, we move on to connected sets, which is a much more fun topic. When we are dealing with connected sets, which I will put the definition of up on the screen now, things become more fun because you can just visualize this so easy, and it is nice. All right, here, let me take a picture here and get you everything we need. Actually, I won't even take that picture because we can just state this directly and it will be more fun. Okay. I'll draw it. That'll be even better. All right. So definition 1.4.11, a set C contained in the complex plane is path connected if for every pair of points A and B in C, and C the set, there's a continuous map, and this is a gamma, from the closed interval from 0 to 1 into C, the set, with gamma of 0 equal to A and gamma of 1 equal to B. And we're going to call gamma the path joining A and B. So here's the idea. Here's what a connected set looks like. So if I have some weird blob of points, I don't know why I'm specifying the outside of it here. Let me just... Okay, here I've got some weird blob of points. And I've got some A, and I've got some B. Then what we're doing is we're finding some continuous function that goes from A to B, right? So this is A is equal to gamma of 0, B is equal to gamma of 1, and then this right here, that little guy is, this is the graph of gamma. That is, this is gamma of the whole interval from 0 to 1, right? So if we actually just plugged in every single point, you would watch it go through here. Does that make sense? It just continuously moves A, starting at 0, at like, you can think of T as like time. At time 0, it's A, and then we continuously move through our set and get to B. All right. So it seems like this is not a very interesting kind of idea, but it lets you detect things like, for example, in here, I won't even go through and draw like the weird little like voids or something. Let's say that your point A is over here and your point B is over here. So in the previous case, this was our set C. And if instead we're looking at C like this, instead of when C was just this guy, notice C, that's these two guys, right? I'm just putting a box here. to separate it off from the other case, right? See, if C is these two sets, then notice A and B, these are 2 points that are not connected. You can't draw a path. You could draw a path, but it won't stay in C. That is, any way I draw from here to here, I have a big chunk all along there that is outside C. Oh, okay. So path connectedness is a nice way to talk about whether or not there are pieces of subsets. It's just a useful tool to ask what paths can I put on my space or put on my subset, and what does that tell me about the shape of my set. This is a very, very, very common view in mathematics to learn information about an object, look at the functions from, say, like the interval from 0 to 1 to that object. And this is a useful way to detect the structure of what the object is. Look at the maps to it to figure out, what maps you can, what things you can map to it and how you can map them there. Tell you something about what the thing itself is. And that's a useful trick. So path connectedness is useful, though it is slightly different than connectedness. Namely, and I'm going to give you the definition in its gory details. What we'll do instead of, and this is, some people may find this annoying, I think it's a perfectly reasonable way to go about it and is probably actually more instructive, but if you don't love it, I don't blame you. I won't hate you. I guess what I'm saying is that it's reasonable if you find this cumbersome at first. So this is the definition of connectedness. So a subset C of the complex plane is going to be not connected if there are open sets U and V such that C is contained in the union of U and V. C intersect U is non-empty and C intersect V is non-empty, and C intersect U intersect C intersect V is empty. So that is a not connected set. A set that is not connected is called connected. Ah, all right, fair enough. So this looks really messy at first. Here's kind of the idea. Here's what we want to pick up. We want to pick up the idea of, say, like I have like, well, here, let me, instead of drawing all of these nice boundaries, let me use these like little kind of like fuzzy guys like here, and so I don't have to be drawing dashed lines and stuff, right? So here's like a thing that we want to say is like not connected, like this guy, right? Okay, so let's say that this is the thing we're looking at. We'll call this C. Now, the idea here is that we could find an open set U and an open set V. So U and V. I should make that U look capital and that V look very pointy. U and V, such that C intersect, or C is contained in the union, right? The union is everything that's in both of these guys. And to be clear, what I'm saying is that U is all that, and V is all this, right? Try to do the switcheroo there. Does that make sense? So these guys, look, they cover C. They have all of C inside of it. Their intersections with C are non-zero. However, if you intersect their intersections, then you get nothing. So that's a useful little trick. There are lots of caveats, or lots of non-intuitive things that you should always pay attention for, or train yourself to expect, at least, when dealing with topology that is maybe not well illustrated by these like nice little blob pictures. Namely, I'm showing you lots of pretty sets, but like what about these sets, say, missing random chunks of complex numbers, some, finite smattering of points? Does it still hold? Well, now it's not as clear. All sorts of different things like this. You can take out very complicated sets and make it like a Swiss cheese, or like a very fine mesh, and have things become a little bit different. But so don't just assume that because you can draw a little blob, every possible set acts like the little blobs you draw. But it works really well here to talk about connectedness. Notice our picture here with connectedness is pretty similar from path connectedness down to connectedness. This is not that fancy or anything like that. What what this allows us to do, and I think I was just looking for the number of this proposition in your text, is prove proposition 1.4.14, which says that a path connected set is connected. And since I've only described path-connected sets and connected sets for the complex plane instead of in our full gory details in arbitrary topological spaces, proposition 1.4.14 should suggest to you that maybe this is not always the case, right? And indeed, it turns out that it's not in certain topological spaces. However, they have to be kind of interesting. So in terms of our nice things, though, it basically says that connectedness, this property formulated entirely of open sets, the topology, can be detected entirely by continuous functions. So this purely topological property is detected by the types of continuous functions you can put on a space. That's useful. And so it says path connected set is connected. Nice. Okay. However, a path connected set, and this is important, does not need to be path connect, or does not need to be, a connected set does not need to be path connected. That's what I was trying to say. The converse is not true. This is something you should be careful of. So there is a standard example. Let me actually just graph this bad boy for you right here. Here, pull up Desmos, and I can show you it. Okay, so the standard example, I won't be able to actually plot this out as nicely as I'd like. So someone takes the graph of the function sine of 1 over x, and then you do this just for, say, like x greater than 0, and then you grab a nice line segment where you like right here at x equals 0, and you go right over, right? So you can imagine this going right. But because, as you can see, if you've probably encountered this before, since this oscillates a lot, like the more you zoom in, like it oscillates infinitely many times, right? Notice that you can't get a continuous path from somewhere over here to somewhere over here a map from a finite interval to over there, right? Because this thing has to travel like along an infinite distance, right? Like, continually going up, down, up, down, up, down, up, down, right? And it's not even defined at 0, right? So if we hooked like a straight line on at 0 over, then we'd never be able to get to the left-hand side from the right-hand side. See what I'm saying? So that is a connected set, obviously. The line connects all nice, but it's not path connected because the distance is too great for any path to get across. Does that make some sense? So path connected set is connected, but there are connected sets that are not path connected, and these are generally in C or in R2 or R or something like that, are things where you get these pathological like oscillations, and that's a very important little thing. So, however, we have some good properties that are worth covering. Pop a new layer right in here. All right, so the next proposition here, all right, this bad boy. If C is an open connected set, and A and B are within C, then there's a differentiable path from the from the closed interval from 0 to 1 in C, with gamma of 0 is A and gamma of 1 is B. So this says that not only if you have on open connected sets, not only do you have path connection, but there are differentiable paths. So that's kind of cool. Differentiable paths, that's important. Anyways, open connected sets are a big deal, and they give you nice things like this. This property will play a large role later on. So it's worth keeping in the back of your mind, but we'll bring it up again later when it becomes more relevant. But a region or a domain, as people tend to call them, is an open connected subset of C. So some people will use this differently in different contexts, but in complex analysis, if you ever hear someone say like maps the region or maps the domain such and such, what they mean is a open connected subset. And you'll see this all the time. We'll use them synonymously with open connected subset because it's so important, and generally this is because of this nice property up here. And to be clear, to have a differentiable path, this just means that the real and imaginary parts as regular old functions are both differentiable in the standard calculus way. Nothing fancy that you have to feel worried about there. But yeah, so we're going to kind of book through a little bit of the next little business. Actually, we're going to skip over a little bit of it. So they like to go through a few nice facts that are straightforward and we don't need to really work with too much. For example, the continuous image of a connected set is connected. So if C is connected, then f of C is connected. All right, for continuous functions f. And then they get into the real big kahuna for the rest of this section, which is compactness, and that will play a big old deal along with uniform continuity, and then they talk a little bit about the Riemann sphere, and we might even honestly skip over a little bit of stuff about the Riemann sphere and come back to it as needed later on. So compactness, I will give it to you in the less built up way that they do in the textbook, since we don't want to go too far over on a Friday night. They do provide a great explanation, actually, of how they build this up in your textbook. I love this. They go, okay, here's something you're gonna see a lot. What we'll do is we'll provide an easily recognized characterization, a property that we want, and then a technical definition that becomes useful in technical situations. So it's wonderful that they go through it like this. And you should read through this section if you want. But for our purposes, hanging out in C, the complex plane, here is a perfectly reasonable definition for compactness if you're living in C. Closed and bounded. A closed subset that is bounded. That means that if you take the modulus of everything in your subset, there is a max to that, right? It doesn't have things like arbitrarily large things in there. It has biggest stuff. Fair enough. And then it's closed. It's got all of its limit points. All right. Sorry, I had to take a second to take a sip of my Gatorade. All right. So this is they do a great characterization in the book. Really build up to it in I think a enjoyable way. They talk about open covers, which I will give you as a nice little picture, but I won't go beyond it. So compactness is in C just means closed and bounded, but the idea is that compact sets are like points. That's kind of what I'll say. Compact sets are like points or collections of points or something to that effect. That is, if I do a circle and I have everything inside of it, then I've got a compact set. So this will be our compact set. We'll call it K. The standard definition for how compactness works involves, let me make this really big, involves the idea of an open cover. So I'm going to drop back the opacity down on this and then see if I can't just, too opaque. So open cover just means, and I'm trying to make these things look like their own little things. So imagine each one of these is an open set. Open covers are just some open sets, some collection of open sets that cover the space in the way that you would, or the subset in exactly the way you would expect. An open cover is just a collection of open sets whose union contains the set. So if K is contained in C, an open cover of K is a collection of open sets. Let's call these O. I'll say O. Just this big subset of open sets in. I'll write tau, where tau is the topology of the complex plane. So this is a collection of open sets. I do mean to write the containment such that K is contained in, is a subset of the union, and I'll write this, maybe I should make that U look nicer. This is like a big union for, let's just write for U in O of the open sets within O. So I'm saying that if you take a big collection of open sets and you put them all together, then K's inside of it. That's an open cover of K. So it's some collection of open sets that have K inside of it. All right, good. Compactness, in the technical sense, is just this. K is compact if every open cover O has a finite subcover, i.e. U1 through say UN in O, such that K is contained in the union of all these U's. See what I'm saying? Sorry, I got writing a little bit sideways right there. But basically, a compact set just has every open cover has a finite subcover. That is, to cover up the set, all you ever need is a finite number of open sets. All right, you could maybe do it with more if you wanted, but finite is always enough, right? There's no open cover where you can't extract a finite subcover from it. And so that's the technical definition of compactness. It is a beast, I guess. It doesn't look that nice. The best part is that in C, closed and bounded is the same thing. Why on earth do we care about compactness? Well, it's for this very important fact. This is a wonderful fact, theorem, and I believe this is summarized in proposition 1.4.18. Here, every sequence of points in a compact set K has a convergent subsequence. So, and remember, because in C, a compact set has to be closed and bounded, what we can say is has a convergent subsequence whose limit lies in K as well. But that's automatic. So basically this means that, hey, any sequence you've got, maybe it doesn't have to actually converge to something. Imagine that you've just got this K up here that I've now drawn, I've covered with a bunch of weird dots, open sets. You could have like a sequence of points that just kind of keeps going around, right? Around and around and around and around, right? Okay. However, we could grab a subsequence of those points. For example, if it hit the same dots every single time when it went around, then I could grab all of just the dot every time it hits just right here. That's a subsequence, just some elements of the sequence, and it converges to something in K. It might not be a unique point of K. Every subsequence may not converge uniquely to some point, but it always has a convergent subsequence. That's useful and interesting. So if the sequence does converge overall, then you get to have this nice... the existence of convergent subsequence is quite useful, and we'll see why later on for a lot of reasons. Now, compact sets behave nicely, like many of these other things we've been looking at, relative to continuous functions. Like connected sets, the continuous image of a compact set is compact. So you put a path-connected set through a continuous function, you get out a path-connected set. You put a compact set through a continuous function, you get out a compact set. Kind of nice. You also get, and this is the most important thing, this is a very important point that we will use quite heavily in some very, very big deal theorems. In fact, I will just actually write this one out. this is theorem 1.4.20, the so-called extreme value theorem. And the extreme value theorem says that if K is compact and f is a function from K into R, the real numbers, and it's continuous, sorry, if it's a continuous function, then f attains a maximum and minimum value. And maybe I should say a finite maximum and minimum value, but I guess you can't attain an infinite minimum value and still map to R, right? Because infinity isn't a number, right? So maybe that's redundant, but it attains a maximum and minimum value. That is probably the way that most people would say it. Your book throws that finite piece in there. So this is a big deal that we'll use a lot. Continuous functions on compact sets have extrema, finite maxes and minimums, and they actually get there. The idea is that compact sets are kind of like too small to keep for your functions to keep going either up or down forever. They have like a hard edge, and then they kind of have to stop doing stuff, and so there's only so much they can do in between those edges, right? And so this gives rise to a lot of useful things that we'll see later on. Another thing that we'll need later on is the distance lemma. So this lemma I will just copy and paste because why not? We need to move on a little faster. So the distance lemma says that if K is compact, C is closed, and K intersects C is empty, then the distance from K to C is greater than 0. So what this kind of says is that the distance from a compact set to a closed set, if they're disjoint, has to be positive, right? So basically, if K is compact and C is closed, and they are disjoint, then they can't be like right on top of each other. And this might seem kind of obvious, like, okay, if they're disjoint, then yeah, I guess they have to be kind of far away. But for example, consider the distance. If you have one set A, that's the irrational numbers, and one set B, that's the rational numbers, then, well, they always get pretty dang close to each other, don't they? Yeah. So maybe it's not always clear that we can get positive distance just from disjointness. But when you have compact sets, they're at least a little bit a ways away from closed sets. All right, it's kind of technical. It doesn't really give you a lot of intuition into the topology, but we'll use that later. Finally, something that we will use later, and this really brings us to the end of everything, is uniform continuity. Uniform continuity. Well, here, yeah, we'll have enough time to just do this. I'm sorry if we run tiny bit over. Here's the end of the section. We should just finish it anyway. You don't need any of these pieces for homework. So if you're just watching for that, don't worry, you're fine right now. So a definition, this is uniform continuity. A function f from, say, A to the complex plane, a subset of C, is uniformly continuous if for all epsilon greater than 0, there exists a delta greater than 0, such that f of s minus f of t in modulus is less than epsilon whenever s minus t is less than delta. So this looks almost like the regular definition of continuity, but the big thing here is that we are not saying continuous at, like, it's continuous at, say, like s or something like that, right? We're just saying uniformly continuous. So the same delta here works for all choices of s and all choices of t, something like that, right? So if you're within delta of a given point, any given point, then the images of those points are within epsilon of each other. So it says that you don't have to vary your delta by your choice of points. And why do we care about this? Well, we care about it for the following fact. This is a proposition. I think it's 1.4.23. A continuous function on a compact set is uniformly continuous. This is one of the examples of when I was saying that compact sets are kind of like points. Basically, you can think of it like, normally continuity and uniform continuity are quite different. Continuity is like a point-wise concept, while uniform continuity is like a space-wise concept, right? Continuity is local, uniform continuity is global. However, if you're on a compact set, then compact sets are enough like points that local and global property coincide, right? The global property essentially becomes like the pointwise one, right? It assumes the same role. So that's a great example of compact sets basically being kind of like points in a certain topological sense. It's a reasonable intuition to inform how things could work. This will become useful a lot. It's a very powerful notion, uniform continuity. We'll use it with the distance lemma. We'll prove some interesting geometric facts, a number of different little tricks there. We'll be able to gloss over a bit of this since I won't be outlining all of the proofs. I don't have forever to do this, but for some of the more useful facts later on, I will at least try to motivate how the technique of the proof is done, and this will be useful to do so. I highly recommend just getting comfortable with all of the concepts in this chapter, because there are a few things we won't talk about right now. We will instead just bring them up a little bit later on. For example, the path covering lemma, I think if we bring it up right now, it is long and messy. Here, I will pull it onto the screen. I can scroll down to it. You see the path covering lemma right here. Look at the 4 parts and all these messy little pieces. It's not actually bad. Basically, it says that a continuous path on an open set can be covered by a finite number of overlapping disks. Basically, it's like, hey, that's a continuous path on a compact set is from A to B, right? It's got a compact image, right? So don't worry. This is something that we'll bring up later. You don't have to remember this, like, to make flashcards for this. Don't, for the love of God, do that. Instead, we'll just bring it up later on when it becomes relevant to some of the techniques we'll introduce. Then your textbook goes briefly into the Riemann sphere, which is useful and interesting. It's just the 1-point compactification of C, if you're familiar with it, the Alexandrov extension. But if you haven't heard of it, don't worry. We won't really use it much, and there's nothing interesting that needs to be said about it now. It is very simple. Basically, the idea is just, hey, take the complex plane and add an extra point at like infinity, and just kind of imagine like it's like sort of like wrapping it into a ball. But you don't need to care about that now. We'll bring it up later at a few places where it makes certain things more intuitive to think about. You won't have to use it. So that is pretty much all for this section that matters to us right now. I know that a number of people, and if anyone has to go, feel free to go or click off of this video. I know that a number of people ask questions about the hyperbola and parabola questions on your homework. Don't overthink it. It works just about as easily as you think. I encourage you, if you're struggling with it, to send me an email and I will help you out. Yeah, let's end it there for tonight, unless anyone else has any questions. I think we've got through this section sufficiently for the moment. Remember that your homework is due on Sunday at 11:59, so you have the whole weekend to work on it, and you can send me questions if they come up during that time. All right. Well, thank you, everybody. Have a wonderful weekend, and just shoot me an email if you need anything. Cool. I'll see you next week.